Systems of inequalities, otherwise known as linear programming. Some very useful real-life information here. Linear programming is a way that companies use tools, manpower, wages, overhead costs to create a workable budget or a feasible region in which they can make profit in their business, in their company. It's too bad that we don't spend more time on this because it does have a lot of real-life application. Systems of linear programming show a region or a shaded area known as a feasible region where the solution set lies. And so the first thing you need to do is solve equations that are not already solved for y. And remember, you'll be switching the symbol here because you are multiplying by a negative number. And in this case, we are dividing by -2. Then what you'll do is you'll graph these three lines. The vertical line at x equals 0. You will use slope-intercept form to create your other two lines, starting at the y-intercept of 6, down 1 over 3, down 1 over 3, and connect that line there. Then do the same thing here, y-intercept of 0, up 1 over 2, up 1 over 2. I'm using solid lines in this particular example because each of the inequalities is less than or equal to or greater than or equal to. Then I will follow that up by shading the appropriate region. Notice it has to be greater than 0. Notice it must be less than, y must be less than 1/3 x, and y must be greater than 1/2 x. So your feasible region is this shaded area. That means that any solution to this system of linear equations must lie in the shaded region or on the solid lines. The vertices for this are, be nice if I switched my pen, are 0, 0, 0, 6, and 7.2, 3.6. All of which can be found by solving that system of equations. A spin-off of what we will be doing with this is finding the area of that shaded region. Well, we know that that area is triangular, so that's 1/2 base times height. The base of the triangle in this particular instance is 6, and the height of this triangle is 7.2. 6 from here to here, 7.2 from there to there vertically, which means that the final answer to this is 21.6 units squared. Moving down, second example, exactly the same way. Solve the third equation for y. Y is less than or equal to -2x plus 6. Please observe that there is a negative in front of the y, therefore the symbol will be switched because we will be dividing by a negative number. We'll begin with our first system equation or system inequality, and we'll draw ourselves a horizontal line at -4. Now we're going to introduce the dotted line as opposed to the solid line by putting our y-intercept at 2 and going up 2 over 1, up 2 over 1, up 2 over 1. Likewise, I will go in the opposite direction as well, which is probably the more important direction since it intersects with -4. All right, then finishing off with negative 2x plus 6. Starting here, going here, all the way through. And there is our feasible region. However, this is how you know. Must be greater than negative 4, less than 2x plus 2, that's this direction here, and also less than 2x plus 6, below the line. Less than here, here, and here. Again, a triangular feasible region where the solution lies. The solution lies in that set of values. Negative 3, negative 4, 5, negative 4, and 1, 4 are the three vertices to this feasible region. Finding the area of the region, 1/2 base times height, 1/2 8 times 8, which is 32 units squared. All right, moving on. Application of word problems. It's very important for you to see and understand how to translate the English into math. So remember, we've got to have between 5 and 8 representatives from the junior and senior class. So that means that 5 is the least amount of juniors and seniors we can have, and 8 is the most that we can have. Okay? All right, then we go further to see that the committee must include at least 2 juniors and at least 2 seniors. So the number of juniors must be greater than or equal to 2, and the number of seniors must be greater than or equal to 2. There is your system of linear equations. Now please note that this can be rewritten as 5 less than or equal to j plus s, and 8 is greater than or equal to j plus s. Whichever way makes you more comfortable. Okay, you can work at most 20 hours next week. Means that you will be walking dogs or washing cars, and that must be the most you can work all week. The most tricky part about these problems is facing this symbol the correct way. If you get paid $7.50 for walking dogs and you get paid $6 for washing cars, that means that you need to earn more than $92, because it says at least $92 to cover your weekly expenses. And there is your system of linear inequalities. Number 5, please make sure you work this problem before going on any further, because this is the type of problem that involves that business sense that I was talking about, the ability to see where your profits occur, where you lose money, where you make money, how many people you have to employ, all of those things. All right, so first of all, you get $10 per adult and $5 per child, and you want to make more than $600. The total number of tickets that you can sell, either adult or child, must be less than or equal to 100. In solving your equations for C, because this is going to be the axis that I choose as the y-axis, I'm going to rewrite this as children. And this will be adult. Alright, so solving for C, I get C is less than or equal to negative A plus 100, and C is greater than negative 2A plus 120. Now I'm going to graph both of those. starting with this one, 120, down to over 1, to there, and this followed by this one, which is 100 and I'm going to continue it, and you'll see why when we get down a little bit further. Okay, now I'm going to solve this problem here. Would the theater make a profit if 42 adults and 29 children purchase tickets? So 42 is here, 29 is here. The answer to that question is no. And the reason it would not is because it is outside of the feasible region, which lies here. All right, can the theater make a profit if no adults come to the performance? All right, well, let's go ahead and take a look. Okay, if no adults come to the performance, that means 100 children come to the performance. That is also outside of the feasible region, so the answer to that question is also no. Okay, now in order to answer E and F, what we must talk about first is your profit equation. And it just so happens that our first equation was our profit equation. This right here will give us the total amount of profit. Now, the way that you determine your maximum profit is by finding the corners of the feasible region, the vertices, and using those ordered pairs in this. The maximum amount of profit will lie at one of those three areas. So this ordered pair is 2080. This ordered pair is 60-0. And this ordered pair is 100-0. Right? Plugging that into the equation 3 times, you get 10 times 20 plus 5 times 80 for a total of $600. 10 times 60 plus 5 times 0, again for $600. 10 times 100 plus 5 times 0 for $1,000. So now we've answered E and we've answered F. How many tickets of each type must be sold for maximum profit? That is 100 adults and leave the kids at home. 0 children. What is that maximum profit? That is $1,000.